So good morning. This is your seventh lecture on control of espaços de estados, and we have started a chapter related to control by state feedback. And the expectation is that we are able to show that by feeding back the state, you are able to place the poles of the closed loop systems wherever you want. Now, this happens only for some classes of systems, and to clarify this issue, we mentioned two concepts, controllability and observability. And we have introduced the concept of controllability. Let's review it a little bit fast. So we say that state realization x dot equal to ax plus bu is controllable if your initial state is at the origin, x of 0 is 0, and you specify some final state xf that you want to reach, and if you are able to find a control sequence u or a control function u that in a finite time drives you from the origin to this xf, then the state realization is controllable. Now, remark that I say state realization in that system because the same system can have different state realizations. Actually, we have seen that there can be an infinite number of state realizations. So an infinite number of A, B, and C, which is not shown here, such that from the input-output point of view, the behavior is the same. This definition of controllability also usually is also mentioned as the system is said to be completely controllable or reachable. In Portuguese, reachable means atingível, that is to say, from the origin, you can reach any point of the state space. Now, it's not obvious by just looking at the equations that you can find such a function. So you should have some criteria that is easy to check. And I said that this theorem holds. So you build the so-called controllability matrix, which is a matrix made out of the matrices A and B in this way. So you place in the first column of the controllability matrix B, then on the second A, B, etc., up to A, up to n minus 1, where n is the dimension of x times B. So if B is a vector, in the case where you have just one input, this is a square matrix with n rows and n columns. And if the rank of this matrix is equal to the dimension of the state, then the pair AB is controllable. Okay? Of course, this needs to be shown. We are going to show this not in continuous time, but in discrete time, where the proof is simpler, more readily obtained. And then I gave you two examples. In one of the examples, U was not affecting one of the state variables, x2. And this is not a controllable system. And in the other, you had two parallel systems that were equal. And in this case, of course, x1 and x2 are always equal because they start with the same initial conditions and they are driven by the same input function. So you can only reach trajectories along the straight line at 45 degrees. And this is again not controllable. If you apply the criteria, then you also find that the characteristic matrix is not does not have a rank of 2, which is a state dimension. Now, let's consider an example that generalizes these two examples. Suppose that you have a diagonal system. Pay attention. I'm saying a diagonal system, not a system that can be diagonalized. So the A matrix is a diagonal. I call it lambda, and lambda is a diagonal of numbers. Okay, lambda 1, lambda 2, lambda n. And if you write the controllability matrix, you can do a 2x2 example or 3x3 example. You can convince yourselves that what we have is, well, B, then lambda B is lambda 1 B1, lambda 2 B2, etc. Lambda square is lambda 1 square B1, etc. This is very simple because the powers of a diagonal matrix are just the powers of the elements in the diagonal. Okay. This comes straightforward in a straightforward way from the way you multiply matrices. So when do you lose rank? You lose rank when you have 2 rows or 2 columns that are proportional. For instance, if you have B1 equal to 0, then the first row becomes 0. And you only have n minus 1 independent rows at best. So if some of the rows, if some of the B's are 0, you will lose rank. So you lose controllability. Now, suppose that you have 2 lambdas equal, say lambda 1 and lambda 2. Then, so if lambda 1 is equal to lambda 2, what happens is that the first column is proportional to the second, and the constant of proportionality is the quotient of B2 and B1. So again, you have 2 vectors that are collinear, so you lose rank and you lose controllability. So in this case, you lose controllability either because one of the BIs is 0 or because there are equal eigenvalues. This is very easily understandable if you plot the block diagram. So in the case of a diagonal system, you have n separated first order systems, each one with a pole at lambda 1, lambda 2, etc., lambda n. And you have the B's. Now, if, say, B1 is 0, U is not affecting Z1. So it's impossible to take Z1 away from 0. And of course, this state is not controllable. I mean, you can't drive it from the origin. Now, if B1, if lambda 1 and lambda 2 are equal, then Z1 and Z2 are proportional always. So again, there is a direction in which you must keep this proportionality and use again controllability. Okay? This will be important for a conclusion to take later. Any question? Okay, for discrete time systems, you have quite similar definitions. So if you have state realization of a discrete system of order n, then the state equations are written in this way: x of k plus 1 is equal to ax k plus b uk. And we say that AB is controllable in the sense that it is reachable if and only if, or this is not a misprint, this EIFF means if and only if. It's an abbreviation for if and only if. For an initial condition at the origin, there is a sequence of controls U0, U up to capital N minus 1. such that your final state xn is xf for any xf. So you should be able, starting from the origin, to reach any final state that you specify xf by selecting this sequence of control variables. Okay? And this must be done in a finite way. So this n should be finite, must be finite for the system to be controllable. Now, again, you have this criteria of controllability that you see here. So you build the controllability matrix as before. So it's B, A, B, etc., A up to n minus 1B. And for the system, for the realization AB to be controllable, the rank of this matrix must be equal to the dimension of the state. Okay. Now let's prove this in the discrete time case. There is a direct proof. Also in the continuous time, but in the continuous times it involves impulses, which is a bit cumbersome. So let's do it in the discrete time case, which is quite direct. Now, to do the proof, we need the Cayley-Hamilton theorem. The Cayley-Hamilton theory is this. Suppose that you have a matrix and you build the characteristic polynomial of the matrix. So remember that the characteristic polynomial of the matrix is determinant of Si minus A. Okay, this is a polynomial in S, and it's called the characteristic polynomial of A. So let's write it in this way. It's a polynomial of degree n. Now, the Cayley-Hamilton theorem says that if you replace S by A, and this last term where you have S up to 0 by the identity, then you have a true identity. You have a true equation. This this combination of powers, actually a linear combination of powers of A is equal to 0. In other ways, in another way, set it in another way, which is not exactly true, but it gives some intuition. We can say that a matrix is a root of its characteristic polynomial, or a matrix is a root of the characteristic equation, which is the same. The characteristic equation is obtained by equating the characteristic polynomial to 0. Okay? This is not exactly true because S should be a scalar. Okay, so you are changing the category. It seems that, well, okay, this is very easy to show because if I place here S, I replace it S by A, then I get the determinant of the A minus A, which is 0, and this is 0. But it's not so simple because you are changing the category of the variable. The variable should be a scalar, complex number, and you are plugging there a matrix. So this subtlety means that the proof is not obvious. Actually, it's a difficult one, but intuitively it works. Okay. Now, what does this mean? This means that if you know the powers of A up to order n minus 1, then you can compute an without multiplying the matrix A, just by making a linear combination of powers, of these previous powers. Okay. That is to say, if you think of the powers of A, say A up to 1, A squared, A cubed, etc., as vectors in a linear space, then the dimension of the linear space is n, because you can express an as a linear combination of the powers between A up to 0 up to A up to n minus 1. So these first powers form a basis, and you can express an as a linear combination of them. And for an minus 1, you can express it again as using the previous ones by working recursively this argument. So you can express any power of A as a linear combination of these first powers. Now, let's use this Cayley-Hamilton theorem to prove this lemma, that the rank of this matrix, you see, this looks like the characteristic matrix, but you don't stop at the order of the system. You go, and this capital N is bigger than the order of the system, okay? And what happens is that the rank of this larger matrix is the rank of the characteristic matrix. So the one in which you stop at the power an minus 1. It's not difficult to see this because we could anticipate this result, because the powers of A, due to the Cayley-Hamilton theorem, are a basis in which you can express higher order powers. So let's do the proof. We start by using the result from the Cayley-Hamilton theorem that states that there are polynomials A1, A2, etc., such that A verifies an equation like this, which is the characteristic equation. So this is nothing more than the determinant of Si minus A with S replaced by matrix A. Now you multiply on the right by B, and you get this stuff. And this shows that A and B is a linear combination of the first elements, of the first powers. And then you consider, you assume that now AN is a linear combination of these first powers. So what about AN plus 1? Okay, and AN plus 1 is the power or the product of A times AN. You express the AN as a linear combination of these first powers. Then you have probably something that is outside this range. So you express it as a linear combination of these first powers and so on. All the vectors A n plus I b are a linear combination of b, ab, a squared b, etc. Now, let's prove the controllability criterion. And for that, let me go to the whiteboard for a moment. So we have our model. Remember that. And we start with an initial condition. So x of 0 is 0. It's a vector 0. So usually I don't put the underscore, but it's a vector. So x1 is what? Is a of x0, which is 0, plus b u0. Now x2 is a of x1, which is a b u0 plus b u1. Now x3 is a of x2, which is this stuff here, so it's a square b u0 plus a b u1. So this is a of x2 plus b u2. And in general, you can go on and you find that x of n is what? A n minus 1b u0 plus a n minus 2b u1 plus etc. up to b u n capital N minus 1. Okay, this is an important result. It's very simple to obtain. It shows that the state at time n is a linear combination of these vectors, this vector, this vector, this vector. Okay, and the coefficients are u0, u1, u2, etc., up to un minus 1. So you can express any vector as a linear combination of these vectors, provided that they are a basis. But you know that if n is bigger or equal to n, then actually you can find the first ones of this vector sequence form a basis for the state. So since they form a basis of the state, you can express any vector by a linear combination of them. Okay, and this is the basis for the proof. So let's go back to the slide. Okay, so this is the formula that we have deduced in the whiteboard, and it says that xn is a linear combination of these terms b, a, b, etc., up to a capital N minus 1b. But we know that the subspace generated by these vectors is the same as the subspace generated by the first vectors, where the powers are only up to the order of the system. Because for higher powers, you can express them in the first ones. Okay, so if the rank of the matrix formed by putting this into columns is equal to n, that is to say, if these n vectors are linearly independent, you can reach any state by selecting the u's, u0, u1, etc., up to un minus 1. More, for the least time that you need to reach any point in space is the order of the system. So if the system is, say, of order 2, with 2 kicks, you can reach any state. Okay? Of course, these kicks can be very high, and in practice, if you want to reach some state, you can, if you have more time, you can divide the energy of the kicks but that is another story. The important issue here for the proposals of the controllability criterion is that in n steps where n is the order of the system, you can find a control that reaches any point that you specify. So if you replace x of n by some desired value, the system of equation always has a solution in terms of u0, u1, and un minus 1. Okay? So in discrete time, in discrete time, you have the proof is very simple, and it's constructive. So you can explicitly build or write a system of equations to reach the final point. Any question about this? Well, now let me confuse you a little bit more than you are. And maybe I could have considered a different problem, which is I am at some state and I want to drive my state to the origin. Okay. Now, suppose that we are in discrete time and your system is order 2 and you are initially at the point alpha beta. Okay. Now, is there a control sequence such that starting from alpha beta, you can drive the state to 0? This is one problem. And the other problem is the pair AB controllable?
You can change the derivative of x of 2.
Be careful, because here we have no derivatives.
Okay, you can change the next state of x2.
So what you mean by that? You must be more clear. I'm not understanding you.
So the matrix A in the second line is all zeros.
Okay,
so
it naturally goes to 0. So what is the equation that you must solve to find a new? So you are at 0, 0, no? You start at, sorry, you are at alpha beta because you are here. So what is the equation? Let's write it in the whiteboard.
We have, Professor, I think we have to equal it to 0, the equation we have, so that the x1 k plus 1, which will be x1, is
Yes.
0, 0.
Good. So let me write what you are saying. So it was x1 k plus 1 and x2 k plus 1 is equal to 1. It was 1, 1 and 0, 0. Am I right? Matrix?
Yeah, exactly.
Yes.
x1k and x2k plus, and it was 1, 0 uk. So you're saying that what should be 0?
X1 k plus 1 and x2 k plus 1.
0 and 0 should be equal to 1, 1, 0, 0.
And then we can put
times, and here what shall I place?
alpha beta.
Alpha beta plus 1, 0, and then you have your U0, no? So this means that you should solve alpha plus beta plus UK plus U0 equals to 0. And then the other one is trivially verified. So 0 plus 0 plus 0. Sorry, 0 equals 0 plus 0. This is the second equation. So U0 should be what? Very simple, no? Minus alpha plus beta. Good. So you understood this. Okay? Now, this means that in this system, now let's compute the controllability matrix. What is the controllability matrix? The controllability matrix is B, AB. No, the order is 2, so I stop at the first power. So this is what in this case? 1, 0, and then you multiply A by B. So this is, again, 1 and 0. So what is the rank of the controllability matrix?
1.
Is it controllable or no? So this is smaller than the order, not controllable, right? So if you have if you start here at some point and you want to go here, okay, it's okay. Just select, it's okay. Just select U0 equals to minus alpha plus beta. But if you are at the origin and you want to go here, impossible. Because the system is not controllable. This means that from initial condition, you cannot drive it away. So you can drive the states to the origin, but once you are at the origin, you cannot go take state number 2 out of the origin. It's something trivial because x2 of k plus 1 is 0 always. Okay. So saying that I could have considered a definition of controllability in which instead of saying you start at the origin and you are able to reach any state, I could have said I start at any state and I could always be able to go to the origin. Now, these two things, these two definitions are not equivalent in discrete time. Sorry. These two definitions are not equivalent. Okay, that's why I mentioned that controllability, in the sense that we said, is sometimes called reachability, atingibilidade, because you start at the origin and you should be able. And it's this reachability that is depends on this criteria of this criteria here. Okay, this criteria here. This is the one for reachability. If you look in books, sometimes things are a bit messy in this way. Now, the interesting thing is that in discrete time, the two concepts are different. So reachability and being able to drive the control to the state to the origin, they are not equivalent. But in continuous time, they are equivalent. So in discrete time, they are not equivalent, but in continuous time, they are equivalent. Okay? Remember that I mentioned to you that the story of if you have x dot equals to ax plus bu, then you can, if you are at some time t0 and you want to go to some time t, so you say that xt is a matrix that multiplies by x of t0. Okay? But in continuous time, it is also true that x of t0 is the inverse of t0, of t0t, sorry, of tt0. The inverse times x of t. So the first one goes from here to here, the second one goes backwards. And this is because this phi in continuous time is phi of t, t0, is nothing more than the exponential of a t minus t0. And this is always invertible, always invertible. Now, if you have x of k plus 1 equal to a x of k plus b u of k, then, okay, I'm forgetting about this term. Okay, I'm just considering the homogeneous term. Then x of t is a t minus t0 multiplies by x of t0. And this may not be invertible. Okay, so the power may not be invertible. And this means that if you know the state at time t, you may not recover the state at the previous time t0. So in continuous time, if you know the state at one time and you know the state transition matrix, you can always retrieve the initial state, but not in discrete time. So in discrete time, time is not reversible in this sense. Okay? And this major difference is related to this issue that we find that the definition of controllability of starting at the origin and being able to go to an arbitrary point in continuous time is equivalent to say start at an arbitrary point and go to the origin. Okay, so these two definitions are equivalent in continuous time, but not in discrete time. Okay, and controllability is the strongest notion, refers to being able to start at the origin and go to some arbitrary point. Was it clear? Okay. So let's go back to the slides. Let me recover my watch. Okay, this is what we have been said. Now, another notion is the notion of stabilizability. Okay? We say that state realization is stabilizable if there is a state feedback, so a nu equals to minus fx, such that if you replace u by minus fx, then you get an equation which is xf equals to a minus bfx. And you know that the poles of the system are the eigenvalues of a minus bf. So if there is an f such that a minus bf has all the eigenvalues with a negative real part, then you say that this system is stabilizable. Okay. Now, can you understand what is the relationship of stabilizability? It's a difficult word to say, even in Portuguese. And controllability. Which concept is the one which is strongest? That is to say, less systems verified. Is controllability of stability or stabilizability? What is if you think of the number of systems that are controllable and the number of systems that are stabilizable, which is the biggest one?
The stabilizable.
Stabilizable. So can you give me an example of a system which is stabilizable but not controllable? Can you invent an example?
Nice question.
Let's pick up one of those simple examples at the beginning. This example, for instance. Now you have x1 is controllable, but x2 not. So you cannot take away x2 from the origin.
Yeah. Okay.
Now, is this stabilizable?
Yes, I think it is.
Why?
It's possible.
Why?
To
Your u does never
Yes.
affect x2.
Oh no. Yes.
So you can design a controller that stabilizes. This is already stable, so even f equal to 0 would work. Okay, because this state x1 verifies an equation which is already apart from the x2. So it would be very simple to do it. Now you have x2. Is this stabilizable? So you design a controller that stabilizes x1. And if x2 is already stable, then it's stabilizable, although not controllable. If x2, for instance, if I replace this -1 by +1, then I would get the derivative of x2 with respect to time is x2. This is a positive exponential. This part of the system becomes unstable. So this is no longer stabilizable because, I mean, you cannot find a nu that forces x2 to go to 0.
Exactly.
Okay, so stabilizable systems are systems for which the states that you cannot control are naturally in the sense that from the beginning asymptotically stable. Okay, so in some cases you have situations like this, that you can divide the systems in the states in two classes, and one class of the states you can make with them whatever you want, so you can drive them to all the positions that you want, and the other part naturally goes to 0, so they are stable by themselves without you to do nothing. Okay, yes. So sometimes this is useful in theorems that you want to prove something for stability. you cannot ensure controllability. Usually it's an ingredient. And but it's not controllable. So sometimes it's not controllable, but you can show that it is stabilizable in the sense that the states that you cannot affect, they are naturally dying out, okay? Okay, so this is all very abstract, no? But let me introduce another concept. Okay, this is important. And it's a good exercise for you. So suppose that you have, and this will be important not today, but in next class, so Friday. Suppose that you have a state realization x dot equal to ax plus bu. And then you do a transformation of coordinates. So you have a new state z, and x equals to tz, and t is an invertible matrix, okay? So you can write z as t minus 1x. T is a square, an invertible matrix. Now, suppose that AB is controllable. If AB is controllable, then you can, then the controllability matrix associated to AB as rank n. Okay. Now, I want to show that when you write the state model for Z, it is also controllable. So if AB is controllable, the equations that form the state model for Z are also controllable. Okay. And I would like to, for that, I would like to relate the controllability matrix in the new coordinates. I call it CZ. Okay. So what is the first thing that we should do to solve this problem?
Apply the transformation.
Sorry? Can you
Apply the
repeat?
transformation.
Yes, find the equations for Z according to the transformations. The T is given. So try to find the equations for Z. Okay. So what should we do? Could we do? So we want to find Z dot equal to some matrix times Z plus some matrix times U. What are these matrices? So start by differentiating this and getting an expression for Z dot that depends only on Z and U. Let's go to the whiteboard. No, start doing. The solution is in the next slide, so don't look at the next slide, okay? Try to do it by yourselves. So we have x dot equals to a x plus bu, and then x is equal to tz, which means that z is equal to, with respect to x,
t minus 1x.
t minus 1x. So differentiate z and get an expression for an equation for z. When you are done, raise your hand, please. The ones that have done it, and I see already 2 hands, start computing the controllability matrix in the z coordinates. Write it down, and then try to relate it with the controllability matrix in the x coordinates. So what is the first step to get the z dot? Is by looking what is z. Z is t minus 1x. So z dot is what? The first thing.
T minus 1 x dot.
T minus 1 x dot. But I don't want any x's. So what shall I do?
Now we substitute x dot by the original expression,
Which is?
ax plus bu, and then switch x for t set.
So z dot is equal to t minus 1 a. And now x is tz plus t minus 1 bu. So we have, now this is the new A matrix, and this is the new B matrix. Okay? So what is the core, the controllability matrix in the z coordinates? So it is associated to these red matrices, and this is what? What is the first? What is the first? What is the first column?
T minus 1b.
T minus 1b. And the second?
T minus 1
T
times
minus
A
1 A.
T
T.
T minus 1 B.
T minus 1 B. And this can be simplified to be, I write it here. Can you simplify this expression?
Yeah, T minus A B.
Okay. And then the third one is what?
The third one would be
Instead of
A.
writing a power, you have the new matrix A squared. So instead of writing the square, write it. The new matrix times itself. So it should be what? T
Okay,
minus
so
1.
T minus 1 A square.
Before that, okay, that's probably correct, but before arriving there. So this is
Oh, okay.
way,
Yeah,
the
yeah.
new way, but you have a squared, so
Times T minus 1 A T
AT
T minus 1 B.
T minus 1 B. And this gives you what? T minus 1
T
and
minus
then
1 A square B.
B. Okay. So in general, this will be what? For the other case, for the when you have the power 3. Again, you have tt minus 1, tt minus 1, tt minus 1, so you end up with what?
T minus 1 A powered N.
Okay, so it would be 3 B.
Oh, yeah. B.
Okay.
Yeah.
Up to something. Okay. Is it
Yes.
clear for everybody? Remember that the controllability matrix in the x coordinates is B, AB, A square B, etc. up to AN minus 1B. Now here, let's call it alpha and beta. So the controllability matrix in the z coordinates is the same thing. So beta, then alpha beta, then alpha squared beta, etc. up to alpha n minus 1 beta, where alpha and beta are these matrices. Now replace them, and what you get is t minus 1b, then t minus 1ab, then t minus 1a squared b, etc. Okay? Because when you do this, remember that alpha square is alpha times alpha, no? Alpha cube is alpha times alpha times alpha, okay? So when you do these multiplications, you always get these pairs t minus 1 that simplify to the identity matrix, so you can delete them. Is this understood? If you don't understand, then you say nothing. São nabisos folhas de hortaliça, pá. Todos, rapazes e raparigas, pá. Se não estão a perceber e não dizem nada. Okay, so let's write.
Teacher,
Yes.
when we do alpha square, the d minus something wouldn't be squared too.
So you have t minus 1 alpha t. That's the first alpha.
Oh, okay, I see.
And t minus 1 b. That's beta. Now you have here alpha, and you have here alpha. So this is the alpha square.
Yes.
And you have here beta, and so on. So now the multiplication of matrices is associative. So you can associate t with t minus 1, t with t minus 1, that collapse, and you get this simple expression.
Yes.
Okay?
Thanks.
More questions? Don't be afraid of asking questions.
In this case, why do we go to alpha square? So why isn't it just two terms like previously?
Beta is this one. Okay? You agree?
Yes.
Now you have then the first one is alpha beta.
Yes.
Alpha and beta. Now you have alpha squared, but you can write alpha squared as alpha times alpha. That's the same thing. 5 ao quadrado é 5 vezes 5, não é?
Sim.
And if you write it in this way, you can take advantage of the fact that this tt minus 1 simplifies to the identity and disappears. That's why I write it, instead of having a power, I write it as a product, which is equivalent. You agree?
Yes.
You understand it now? Estás a perceber agora?
A minha pergunta era só porque é que temos um termo de A ao quadrado? Eu percebo que o termo é esse, mas porque é que nesta controllability matrix temos que ir até ao terceiro elemento?
It's in general. You go up to t minus 1, a, n minus 1, b. It's a general result. Can you give me 5 minutes so that I open the door to the gas man who is bringing the gas? Otherwise, I will freeze. Do you mind?
Of course.
Thank you. Okay, here I'm again. So these were the first general terms, and we should go in general to t minus 1. We should go to alpha, sorry, to beta, alpha n minus 1, and that's it. Okay, in general. Now it depends on the value of n. Is it clear? You understand?
Yes.
Okay. So let's write the expression for CZ in a cleaner way. Okay. So I pick up my eraser, and this simplifies to what? So t minus 1, a, b, t minus 1, a square, b, etc. up to t minus 1, a, n minus 1, b. And let me clean the stuff here and this stuff here. Now, I would like to relate the controllability matrix in the z coordinates with the controllability matrix in the x coordinates, which is here. So what shall I write? CZ is what? This one is tricky. Can you relate both CZ and CX? Pablo, if you know the result, you can tell it. Don't you have some temptation to write something?
Temptation would be a t minus 1 times the controllability matrix, the original one.
B, AB, A square B, A n minus 1 B. Now, does this matrix in this line is equal to this matrix in this line or not? Can you justify this step? It's not putting t minus 1 in evidence because t minus 1, this is not a sum. So how can we justify this? Suppose that
because of the
Is
Sorry?
it a property? Is it a property?
It's a very fundamental property.
because the multiplications by
It's a multiplication.
columns.
It's a multiplication definition, no? Because you multiply t minus 1 by each of these rows to get the product. You multiply t minus 1 by b, t minus 1 by ab, because you multiply rows by columns. So you multiply all the rows by the first column, and you get the first column. Good. T minus 1b. All the rows by the second column, t minus 1 ab. Okay, you get that column, and so on. So it's just the definition of multiplication. Okay, you accept that? Okay, no one dares to define me. So CZ is T minus 1 CX. Okay. Okay. Now, we would like to say something about the controllability in the Z coordinates. What can we say? In this case, these matrices are all square. So what can you say about the determinant of CZ? It's the determinant of what?
T minus 1 times
CX. And this is the determinant of the product of two matrices.
I think so.
It's the product of the determinants. So you can write that this is the determinant of T minus 1 and the determinant of CX. Now, what can you say about the determinant of CZ? It's the product of two numbers, the determinant of T minus 1 and the determinant of CX. So for CZ to be controllable, what must be, what property, what can you say about the determinant of CZ? It must be what? Should be what? For CZ to be controllable, the determinant, the rank should be n, so the determinant should be
n divided by the determinant of CX.
different from 0.
Okay.
Okay, different from 0. Can you say that the determinant of CZ is different from 0 from this formula? So you have the determinant of CZ, and it's a product of these two determinants. What can you say about these two determinants? Let's start with the determinant of CX. By assumption, CX is controllable. AB is controllable. So the determinant of CX is different from 0.
Exactly.
What about the determinant of the inverse of T?
Also different from 0.
Because it's an invertible matrix, so it has rank, full rank. Okay. So the product of two numbers different from 0 is different from 0. So the determinant of CZ is different from 0. Okay. This looks like a very complicated, simple thing, but it's very simple. So the controllability, the determinant of the controllability matrix in the Z coordinates is different from 0. So in the new coordinates, it is the new coordinates, the state realization is also controllable. So if you start with a controllable realization, you do change of variables according to an invertible transformation, and you still have a controllability matrix. Okay? And you still have a controllable system in the new coordinates. That's the result. Okay? Everybody understood? Now, there is one thing which is even better. There is one thing which is even better. Let me clean this stuff here. Now, suppose that I give you, I consider this problem. I give you the equations in X and Z. Okay. And so you can compute the controllability matrices in X and Z coordinates. So you are able to compute CZ and CX. Can you find a link between the states? That is to say, is there a mapping between X and Z? Is there? I give you.
It's just a reference transformation.
Yes, but what is the T?
The difference between them?
What difference? The difference?
No, I was saying the X space of
Now,
dots.
multiply everything here by T. What you get? You get
you get T
if you T
CZ
CZ
equals to CX.
CX CX. But now what you want is T. So T is what?
Oh, CX times
No,
C minus
CX
Z.
C Z inverted. Okay. You see? So this is something which is quite interesting, because if you have two state realizations of the same order, you can relate them by a transformation in which the transformation matrix is this one here. Okay. Let's go to the slides where this is in a cleaner way. So if I give you, if the problem we solved was, we started with the x coordinates, then I did a change of coordinates, x equal to tz, and I could relate this line here, the controllability matrix is in Z, with the controllability matrix in X, this one, and the T. So, and I could conclude that if I start with a controllability matrix with a controllable system, if this has rank n, then this will also have rank n. So if in the x coordinates the state realization is controllable, in the z coordinates that correspond to making a transform of coordinates, then this will always also be controllable. But then I'm seeing this the other way around. So I'm giving you equations for x and for z. I know that they are both controllable and assume that they are of the same order. Okay, then you can relate x and z with a transform of coordinates given by the controllability matrix of A times the inverse of the controllability matrix of Z. Okay, so this establishes a link between controllable realizations, state realizations of the same order. It's a quite remarkable thing, and later we are going to use this to deduce a formula to compute the gains of controller. Okay, was it clear?
Yes.
Okay, thank you. So what are we going to do next? Not today. Today we are going to finish in 1 minute, but the next chapter will be, now look at the story of the observability related to the capability of estimating the state. And then we will look at what happens when we have simultaneous controllability and observability. And we are going to show that if you have controllability and of observability, you don't have any pole zero cancellation. Or if you want, if you have a transfer function with a pole zero cancellation, then either your state realization is not controllable or is not observable. Okay, so there is a link. This establishes a link between the input output models given by the transfer functions, and the state model and the state equations, and the properties of controllability and of observability. Okay, so that is something that we are going to study next Friday. Final quick question. If not, yes,
teacher,
yes.
What is the practical use for the last equation?
For this one,
Yes.
we are going to do this. So when you want to, suppose that you want to design the feedback gains, okay? So you do a feedback of the state, you want to have a formula that you impose the poles, so you know where you want the poles, and you want to compute the gains, okay? Now, there are some state realizations for which the problem is trivial. So what you do, just to show you in one. What you do is this. You start with an arbitrary state realization, okay? And it's difficult to find the gains. So what you do, you do a change of coordinates, and in the new coordinates, it will be very easy to design. If you select these new coordinates carefully, it will be very useful to design the controller. So then you invert the transform. And the transform is actually obtained in the way that we are using this formula that we have just shown today. Okay, using this formula that we have shown today. Okay, so this is one of the uses. There are other uses for this. We won't explore the other uses, but there are other uses. This is, anyway, the fact that you are using this for design is a powerful tool. Any other question?
Not for me. Thank you.
Okay, so we see each other Friday. Bye-bye.
Bye, teacher.
Bye bye. Thank you.
Bye.
Thank you. Bye.